Hi, good evening, everyone. Hope you all are doing well and hope all your families are also doing well. And hope you're having an amazing day. So don't worry, even if you've not been having an amazing day, because we plan to make it better in whatever way we can. Firstly, I'd like to thank everyone to take out the time and join our webinar session today. As you guys already must be aware, today's webinar is focused on addressing some of the common questions people have regarding machine vision solutions, and hoping that some of these questions would help resolve the doubts that you had too as well. Also, we plan to keep a small segment at the last, wherein you could also sort of type in your questions if you had, in case some of the questions are not addressed already. So yeah, sure. On that note, I'd like to kick off today's webinar with a small introduction about our panelists. So we have firstly Mr. Lucas, who's a senior, who's a veteran rather in the manufacturing industry. He worked with companies like NVIDIA in the past, and right now he's working as an advisor for Qualitas. And apart from Mr. Lucas, we have our MD CEO, Mr. Raghava, again, who used to work with Microsoft previously, but then went on to start off Qualitas about 12 years back, and has been working on a lot of successful industrial projects since then. So on that note, I'll hand it off to Mr. Lucas to get started with the webinar. So over to you, Mr. Lucas.
Okay, good evening, everybody, and thank you for joining this webinar as late as it is in the evening today. Thank you, Aditya, for the introduction. Everybody can hear me well. Aditya, could you just tell me quickly if the audio is available to you?
Yes, it is.
Okay. So we are going to be having an action-packed evening today with a bunch of questions, some of which are from us, some of which are from the audience who have asked it earlier. And we're going to keep this as engaging as we can. Very happy to have the opportunity to discuss and talk with Mr. Raghava Kashyapa, who has a wealth of experience. Aditya started off by saying that I have a lot of experience, but actually I think Raghava has even more experience than me in the world of manufacturing and in the world of computer vision in that space. So I hope we can take good advantage of that and keep this lively and informative. So let me start this off by making a certain observation. I've been looking at all the buzz and all the excitement around this world of machine vision, artificial intelligence, Industry 4.0. And when you go to the net and when you try and make some sense out of this, and just to look at what's happening out there and what the opportunity is, they give you a lot of very impressive statistics on how big and how large and what a big deal this is. And let me just tell you one or two of these that I've picked up. According to the highly respected management consultancy McKinsey & Company, in July 2019, they say that the benefits of defect detection and other Industry 4.0 applications are estimated to create a potential value of 3.7 trillion. That's not a billion, but $1 trillion USD by 2025, which is just 4 years away for both manufacturers and suppliers. And there are similarly other equally impressive statistics. Another management consultancy says, and this is Deloitte, on the survey of AI adoption in manufacturing, they say that this market in 2025 is 800 billion. Not as big as what McKinsey said, but almost as big. I mean, a very impressive number. And there are many others which I won't bother you with, but the fact of the matter is that there is a lot of buzz and a lot of excitement revolving around this today. And so to start this off, I would like to try and understand a little bit more of what these people are talking about. And maybe you people in the audience are equally interested in doing that. So when you talk about defect detection, when you talk about a computer vision system based on modern day AI, and there are various definitions of that, what exactly is this? What are the parts of a vision system in quality inspection? Is it just hardware? Is it software? Is it services? Is it a combination of all those things? Could Raghava please start this off by giving us his perspective on this query?
Yeah, thanks, KL. Thanks, Adi, and thanks everyone for attending. I'm really excited to join, have everyone be attending and listening in, and hope someone, all of you take away something of value during this conversation. So I'm really looking forward to this Q&A session. So, these numbers are astounding, KL, in terms of trillions and billions. And I think primarily, if you look at it fundamentally, I like to simplify these things to, what a human does in a manufacturing shop floor. So today, there are some statistics and let me set some context as to why these numbers are really large. Well, firstly, if you look at, industries in general, across different industries, I'm talking about energy, IT, manufacturing, industrials, a number of these industries, one of the key metrics that gets measured is average revenue per employee, which shows, how productive employees are in creating value to the company. So if you are looking at energy, for instance, the average revenue per employee generated by an energy company like Shell, or in India, Indian Oil, or wherever, it's somewhere around $100,000+, right? So, and similarly, for each of these industries, you have this average revenue per employee. Now, it turns out that industrials and manufacturing has the lowest. So in other words, if you look at revenue per employee generated, industrials is kind of at the bottom spectrum of that whole range. So what does that mean? That means that the automation, or how utilized the employee in this sector is, which begs the need for automation, right? So you need to automate because you need to increase output per employee. The only way to do that is to automate certain things that are happening. So you have the same number of people, but you need to do more, generate more value, generate more revenue, right? So you either make those humans really, really efficient, or you have to bring in machines. And if you look at manufacturing workers today, they're as efficient as they can be. People are assembling things, inspecting things, and really, really fast. They're highly trained. But yet, you're at the bottom end of the spectrum. So the only way out is to automate. And so when you look at that automation and the potential for automation and the GDP of manufacturing in the context of the larger picture, it's huge. And that's why this survey data and these stats kind of have an intuitive backing to these large numbers. So having said that, there are two things that humans do. There is, in a manufacturing, they use their motor skills, which is their hands, their legs, they move themselves and move parts and boxes and all the things that go into the supply chain of manufacturing. They're moving things, right, fundamentally. So they're using the machine motor skills. The second thing they do is they use their cognitive skills. And their cognitive skills is the use of their eyes and their brains when they look at how they observe and they apply their judgment in order to take decisions. Now, and we know that robots and automation and material handling equipment, conveyors, and all that good stuff is going to replace the motor skills. But what about the cognitive skills? And the cognitive skills and the visual skills is what machine vision attempts to automate. And so when you look at it and you look at it in that larger picture, there are these millions of factory workers doing one of the two, applying motor skills or their cognitive skills. And just like, and it turns out that the motor skills is actually easier to automate. It's easier to replace the human hands and legs, because it turns out that we as humans aren't really that, motor skills aren't our strengths, right? We are probably really weak when it comes to a simple conveyor. A simple pick and place can far outdo an average human in terms of lifting things or moving things or assembling things. So that is kind of really getting outpaced in terms of innovation and automation. And there are stats that are going to show that how robots are going to explode in the next 4 to 5 years. But what about the cognitive and visual skills? And it turns out that's really the strength, and that's much, much harder to replace, because even a simple task such as looking at a misplaced item or a scratch on any kind of surface, a 5-year-old can identify it. But trying to teach that same scratch detection with a machine is much, much more difficult than one would imagine, right? And this is the kind of challenge, etc., that machine vision tries to automate or replace. So when we look at machine vision in that context, and so that sets a little bit of context as to why it's so hard. Let's look at what are the different parts, right? And now let's take an example of a cell phone manufacturing unit, right? Now there's a number of things that go into how a cell phone is manufactured. You have all these different parts. You have the case, you have the body, the electronics that is inside that, and then you have a glass screen, all three of which gets assembled and sort of sealed, right? Now, and these are happening in a sequence at a very high throughput, this repetitive sequence. So there's this one person is just placing screens with the glass screens on top of the body, and they're doing it, 1 per minute or even less, even faster. Now, when you want to automate this visual inspection, you're trying to replace this visual and cognitive skills. So a person is also looking at the screen and making sure that it's assembled correctly, there are no scratches, and it has the right labels or stickers pasted on it. So those are 3 operations that a human is doing. Now, what goes into that is, firstly, the parts are moved in front of that human. So he doesn't go and move to all those different phones. The phones are being moved in front of the human, right? So there is this material automation or material handling that is happening that aligns the part in front of his eyes, right? So that's really the first step, or the fundamental requirement in order for us to even begin thinking about machine vision as a solution. You need to have consistent material handling. Otherwise, it's going to be extremely challenging for us to automate any kind of visual inspection. Then let's look at what is the second step. The human, the operator, is looking at that part. So he's using his eyes, and he's visualizing that, right? And there is, of course, the human eyes has a lot of complexity built in, but that's, if you look at how one could automate that visual capture of that information, it's cameras, right? And we have a multitude and advanced camera systems that can easily and much more clearly image the parts in front of them. So it turns out that the human eye can discern something which is as small as 50 microns, something as small as a human hair, or about a third of a human hair. Now, you have camera systems today that can do many orders of magnitude higher in resolution. And so that's the second part. It's the image acquisition system, or the imaging system. Now, of course, there are a few other parts that complement cameras. You have the optics, you have lenses, you have lighting. You need to have, of course, the electronics to convert the optical images to digital information, and those are the sensors. So all that goes into the image acquisition system. And the third thing that a human worker does is after he sees, he takes a judgment. And it's the decision making which is his brains, right? That's the third element. And the third element, in the automation world is the software. So from that image, there is some kind of a decision or an output that comes out from that processing, that image processing. And that has traditionally been, program based with complex scripting and rules and programs with OpenCV, Python, or these commercial image processing softwares. But it's now being slowly replaced with AI or artificial intelligence. So it's that human intelligence which is then being replicated into machine intelligence or artificial intelligence, as what's very popularly called. And so that's the third element, which is the intelligence or the software or the image processing or whatever you want to call it, right? Now, if you put these three together in various shapes and forms, you can pretty much automate or resolve any kind of visual automation inspection problem in a combination of these three elements. So that's kind of a long-winded answer to your question, KL, but those are the three, basic elements, and that's what constitutes a machine vision solution.
Well, thank you. Thank you very much for that somewhat long but very informative answer. I hope the audience got something out of it. I just want to remind the audience that we can see all your good evenings on the chat window. And thank you very much for that. But we'd like to see some questions as well, because while Raghav and I are totally engrossed in this chatting that's going on, we do want to keep you in the loop. And unfortunately, we can't be all at the same place. So the best way for you to do this is whenever something that either Raghav or I say sparks some kind of curiosity or some thought process in your mind, and you have a question on that, please fire that away and I will see it almost immediately and I could ask that next. Now, there was so much in Raghav's question, Raghav's answer, and I can think of many points that I would like to make in response to that and keep that thread going. But given that we have limited time, I'd like to restrict this to just one or two. And so the one that comes to my mind is this. You mentioned three areas. You mentioned machine automation in terms of material handling and moving parts into where they should be. You mentioned the imaging systems, and then you mentioned the cameras. Now, as Aditya said, I'm an old timer. I've been around for decades. And I can tell you that even 30 to 40 years ago, I remember seeing pretty impressive things in factories with regard to the first two, with regard to robots, as the way GM and Ford and Chrysler and those companies used it way back in the 80s and the 90s. Same thing is true about cameras. I know we have digital cameras today, but the whole concept of imaging has been around for many years. So that leads me to believe that the real trigger in this, why so much of interest and optimism and hope has exploded in the last 7 or 8 years, is not those two. It's probably something in the software. And I think you alluded to that, saying the old software and the new software. So very briefly, can you tell me if I'm correct on that, and whether it is in fact this big black box that they call artificial intelligence, and God forbid others frightening words like machine learning and deep learning and all that. Is that where the real advance and the real explosion of interest has been?
Yeah, that's a great observation, KL. You're absolutely right in the sense that when we talk about material handling, we allude to other, I'll throw up some other industry terms, buzzwords. We have this industry 1.0, 2.0, 3.0, and 4.0, right? And if you really think about, what those are, those were really the levels of automation that got introduced into factories, right? So you have Industry 1.0, which really mechanized things. You had the first level of mechanization in terms of using tools and machines to automate certain things. And it really started in the textile industries back in the early 1800s, right? So, we had mechanizations in textiles, which really led to sort of industrialization. And then we talk about 2.0, these were, triggered by almost all kinds of control systems and automation and robots and skills like that. And 3.0 was more about, the assembly line automation and, the connected systems. And now we're talking about 4.0. But when it came to the human element of it, the first revolution of industries were far superior and had a very disruptive effect. But when it came to machine vision, it didn't even make a dent. There was none of that really, which was even seen in the first three generations of this industrialization. And it's only until much later, which now you're seeing really advanced processing that can be automated by machines. And it's only because of software, and because machine were smart, they were quite capable. The second part of this was image acquisition, which is the cameras. And we had cameras even back 20, 30 years ago, which were even better than the human eye, right? So you had machines that outperformed humans. You had cameras that outperformed humans. But it wasn't until the last 3-4 years when, the scary deep learning, as you put it, the terminology, really matured and came out of these incubation labs and research institutes of the very large corporations, that it started to have an impact in day-to-day adoption. And so you really needed to get the software to the level of intelligence that a human had. And that took decades and decades of innovation. And we are here today. And in today's world, human intelligence is being outperformed by machines and software, and thanks to artificial intelligence and advances. And there are many reasons for that. There were access to data, improved algorithms, very high-end compute. But it's really that third element which was the missing piece, which kind of triggered an inflection point to gain mass adoption. And that's what's contributing to this, fast-paced adoption.
Okay, thank you. That makes sense. That sort of confirms what I've been thinking for some time now. So let me switch track a little bit and get down to something a little more specific. You talked about machine automation, you talked about cameras, and you talked about software. Now let's pick up the middle one, the camera part of it. And this is a question that many people have asked, and I think I know the answer to it, but I'd like to hear it from an expert like you. Why is it that so many of these defect detection, computer vision-based defect detection systems demand specialized professional cameras? And why isn't it that the ubiquitous video cameras that you see all over the place, right from home surveillance to retail store monitoring to airport surveillance to everything else, can be used? Are they just of low quality? Are they not of sufficiently high fidelity? Why is it that people insist on replacing all those, sometimes at a considerable cost, in order to do this?
Yeah. That's a question we get asked quite a bit. And it's actually, the answer is not as simple as the question is. So fundamentally, a camera is a camera. It takes a digital image and it just stores it in a digital format. So why do we need specialized industrial camera, and why can't we just put whatever cameras we get out there? We have webcams, we have these spy cams, which cost less than $10. And why do we need specialized industrial cameras? And the answer to that is, it's not really the sensor, because if you look at what is an industrial camera today it's fundamentally a camera is internally the same. It is nothing but conversion of light energy to electronic energy. And you have basically, if you look at it from a fundamental physics perspective, it's one photon which converts to one electron, right? And it's just doing that. And how efficiently it does it is also a quantum efficiency in terms of how efficient that conversion of energy happens from light to electronics to electrons. So, but what makes an industrial camera different is, the quality of the images that you see from any of these consumer cameras are actually much, much better. You have very high resolutions. We talked about, we see Samsung coming out with a 108 megapixel camera recently. And we're talking about all these SLRs and webcams, HD resolution. So it's not really the resolution or the clarity of the image as you see it to the naked eye, or to save it on any social media or Instagram account. It's the electronics and the software programmability of these cameras which make it very suitable for machine vision. So there's a couple of things. One is you need to have, of course, very reliable form factors to make it withstand harsh industry conditions. So you've seen factories, some of these are harsh. You have dust, you have heat, and they operate 24/7. Now, consumer cameras aren't really designed to operate in those environments. So you do have physical standards that one needs to maintain for the reliability and the conditions that is demanded for an industrial environment. The second is, as we talked about, the vision system inherently is a software-based system. So the software needs access to these cameras in a very reliable and efficient way. And so you need programmatic access. So most of these industrial cameras are meant for viewing live streams, like the webinar that we're having today. I have this external camera that is kind of imaging myself and streaming what I'm talking about, but it's not really meant for grabbing an image using a software and then processing it. So I don't have programmatic access to that. So you need a very strong set of APIs that get supported. And the third is, if you look at how industrial cameras work versus CCTV cameras, etc., it's usually for CCTV cameras or any other consumer cameras, is the streaming rate or the frame rate is usually somewhere around it's good enough for us to view as in a streamed video. Whereas if you're so in other words, you just set it on a live streaming mode. Whereas if you look at an industrial camera, you have these trigger mechanisms. So using the cell phone example, when a cell phone comes in front of the camera, it needs to be notified to take a picture. And so that usually is through some kind of a control system or a trigger, which is a physical electronic signal that goes into the camera and then triggers it. And so you need access not just to programmatic or software access, but you also need electronic access for triggers, etc. And similarly, you may need an output to further trigger something downstream to a control system as well. And last but not the least, you need the flexibility in terms of the optics, because unlike consumer grade cameras, which have fixed optics, which are meant to resolve maybe a certain distance, a machine vision camera, on the other hand, needs this flexible optical system where you may need to have short working distance, long working distances, magnification. You need all the different permutations and combinations, and you don't want to sit and buy different cameras for every application. So it's much easier to buy a single camera, but then just change the lens, right? And that's what um, a machine vision camera offers. It offers that flexibility in terms of the optics as well. So these are all different elements which factor into why one would require a machine vision camera, and that's why those are more popular and why you cannot use like an SLR or a webcam to solve your vision application.
So the answer to this question is, to all these people who are asking whether they can use their consumer level cameras, the answer is unfortunately no. If you want a certain level of reliability and fidelity and accuracy in your computer vision inspection process, you will need to upgrade to these better, more not probably, but most likely more expensive answers.
And in terms of expense, the cost of these industrial cameras are actually coming down quite significantly. So that's one of the trends, that because thanks to the advances in CMOS technology, because, as I said, fundamentally the sensor is the same. It's used across all the different consumer grades and industrial grades. So the manufacturers of these camera sensors are very few. There's Sony, there is IMX, CMOSys, Python, a few others, but they all make these sensors, and that's the primary cost. And we've seen cameras, industrial cameras, be as cheap as a couple of $100s. And so the cost of these cameras are also coming down quite significantly because of these advances. So what used to be very expensive is also getting very affordable, which is also one of the reasons that adoption is gaining.
Okay, very good. We got some questions coming in, and maybe I'll take one at this point. It's from Danush Yu to all panelists, well, certainly to Raghava. And it says, I have natural wheat images taken from Google. So maybe from Google Images. I have to categorize them into healthy wheat and and wheat which is infected with various types of diseases. And so I suppose the rest of the question is, if I want to do this, can I do this with the kind of technologies that you're talking about?
Yeah, good question, Dhanush. Thanks for asking and participating. So, let me kind of answer this from a very fundamental level, because I didn't see the actual question, but yeah, I would also assume, how would you be able to do that? Anya, hold on. Oops, sorry. Yeah, how would you be able to do that is probably the question. And so as I mentioned before, the processing capabilities of a machine vision system like AI is now at a level of intelligence that can replicate human intelligence. So the first question to ask is, if you want to categorize this into the different components, the first question, can a human apply a judgment to do this categorization, or do you need a special instrument like a spectroscopic unit or something else? So the fundamentally is, can a human look at this image and categorize this into healthy versus non-healthy? And if the answer is yes, then the answer to this is yes, you can automate this using AI, right? So that's a fundamental thing, because as I mentioned, thanks to technologies and algorithm advances like deep learning, etc., you have technology which outperforms human intelligence. So it does it faster and actually more accurately as well. So the next question to ask is, now let's going through these three parts of the machine vision that I talked about: image acquisition, image processing. So what kind of cameras do you need so that you're able to acquire images which differentiates to the human eye the different types of good and bad wheat? So if it's no more than just a regular camera, then you should be able to use like a regular RGB camera, take those images, and then have AI to resolve this automatically.
And to continue on that, the idea would be to do this based on deep learning, which means Dhanush would need to collect a large number of example images, both of the natural healthy wheat and the unhealthy wheat with different diseases, and then teach the computer how to distinguish between one and the other well enough that when it finds something that it hasn't seen before, it can, with reasonable confidence, tell him whether it is good wheat or bad wheat. Is that the idea generally?
Yeah, that's right. So AI, the point that I missed and you brought up is fundamentally a process in which it doesn't just AI just doesn't get created. You have to teach the machine to have this intelligence, and the process is known as machine learning. So the machine needs to learn these patterns and these parameters that differentiate something which is good or bad. In this case, various types of wheat defects. And the good thing about AI based teaching, though, is it's very easy to teach. You just give it examples. So you give it a bunch of examples of one specific disease, you give it another example of maybe good wheat. And if you give it enough examples with maybe some kind of augmentation, which, or annotation. So you give hints to the machine by marking the regions which has the defect. Then that's sort of the input for this machine learning system that then processes this into using a very complex teaching and learning methodology to then start to learn what is this defect or what is this diseased patterns, so that in future when you give it something, it's intelligent enough to be able to predict it. And so today the ingredients to machine learning is data being image data. And the more data you can give it, the more intelligent it becomes. So it's very similar to a human, where you learn by experience, except this knowledge is transferable, right? Imagine this human which has this brain, this human operator that's the authority on wheat disease classification. And imagine you can just take this brain, copy and paste it into another human with a simple operation. Well, that's what deep learning and machine learning is. You can transfer intelligence because it's in a digital form. It's a neural network. And then you can replicate it. So you can just clone hundreds of workers who has that same level of intelligence. And then imagine that all these 100 workers are then getting better and better. And then you can combine the 100 intelligence to make it an even more powerful intelligence, and then repeat that cycle. So if you think of it conceptually, this is how AI and deep learning can really work. And it gets better and better and better, and over time all this data is sort of fueling this intelligence, and it's being preserved. You don't need to deal with machines quitting on you or going on strike, or going for a restroom break or a tea break, right? So that's really the power and principle, and it's really translating that vision, and that sci-fi kind of picture is really translating into ground reality as well.
Okay, Dhanush, I think you got a nice long answer to your question, and the short answer to your question is yes, indeed possible to go ahead with your wheat experiment, and we wish you good luck in trying to do that. Please feel free to ask us some more questions, either on that or anything else. Now I'm going to get back to the world of manufacturing from this little diversion we had with agriculture. If we are actually doing a specific computer vision based inspection. And these are parts, these are components in the mechanical engineering industry, maybe in the automotive industry. Can this be used for parts that are somewhat or rather complex with varying geometries?
Yeah. So this is a common challenge where we come across in automotive and consumer goods or in manufacturing in general, especially finished components. So when we talk about raw materials like steel, they're usually in some very basic geometry, like rolled form or sheets or extruded aluminum profiles. They're simpler geometries. But as soon as you start to apply some processes like stamping and CNC and machine operations and welding and all that, you start to make these complex products with complex geometries. And now when you start to inspect these, it becomes a little more challenging, not from a image processing perspective, but really from an image acquisition perspective. Because now you need to image or acquire images across all these different nooks and corners and surfaces for that complex part. And so the approach one can take with imaging or inspecting complex geometries is you either need to have multiple cameras looking at it from various angles, or you need to have some kind of moving camera which moves like a camera which is mounted on a robot, and then it goes and takes images from different angles, or you have to move the part itself. So you got to figure out one of these three mechanisms in order to acquire images, because what you see is what you can inspect. You can't inspect the invisible. If something is on the other, if it's moving on a conveyor, and you need to inspect the side which is touching the conveyor. The only way to practically do that is you have to flip the part, right? And so there is this material handling that needs to be done. So it goes back to material handling and image acquisition. And a lot of times people kind of think of it, oh, can machine vision do it? But it's a lot simpler than one thinks. It's very practical, right? It's common sense. You can't see something which is hidden behind another object. So that's, the shortish answer to, how one would inspect complex parts is you need to have some way to practically image that in front of a camera, and then the software can do this just like it would be doing it for any simpler geometry or a simple part.
There's some good insights in your answer. The first insight I took away was very true. The observation that material in its primitive form is relatively uncomplicated. It's in a roll, or it's in a strip, or some kind of a shape that is not too complex. It's only as it goes through the process of manufacturing that it starts to get complicated geometrically and visually. And the second point that strikes me is that in this example that this person asked about complex parts, and you're quite right. You would have to present the object to the camera in all possible viewing orientations and poses. And that can be a real challenge for a material handling system. So it's quite possible that in a case like this, if you were to look at the relative sophistication of the camera piece, the material handling piece, and the imaging piece, the material handling would turn out to be the most complicated.
In a lot of cases, yeah, especially, if there is high volumes, when you're talking about, one common application is inspection of grains, rice grains, and, very small parts, and you obviously can't look at each grain at a time. So you need a very complex material handling system that images, localizes and separates each grain of rice in front of a camera so that it's able to, inspect each piece. And today there are these rice sorting machines which literally just transport each single grain of rice into various channels, and as gravity kind of drops them to the ground, these high-speed imaging systems are inspecting these grains of rice and then shooting air jets to separate out the ones that have been, discolored or found defective. And the image processing is very, very simple, but the material handling on this problem is extremely complex, right? So because you need to do this in a practically viable way, because you got to inspect, kgs per second to really make this a viable proposition. And so a lot of times these challenges, when it comes in the form of a so-called vision inspection system, isn't really an imaging or a software system. It's really a material handling challenge. And the skills required to solve that isn't AI or software or imaging. It's pure physics and mechatronics and mechanical automation. And so, oftentimes we see that the reason why projects fail or don't really take off is because of that. So there are these imaging experts trying to solve mechanical automation problems, and mechanical automation experts trying to solve computer science problems, which are different words all together. But all three have to come together to form this solution, and that's sometimes where the challenge comes up.
So we started this conversation by talking about a human being's motor skills and a human being's cognitive skills. And we said that we are fast approaching the point where both of them can be done by the computer. It seems like there isn't a general rule that one is always easier than the other, because in the examples that we have talked about now, the effort and the engineering and perhaps the cost that goes for this complex geometry problem that I'm talking about, the effort and cost that goes into handling the part and presenting it in the form that the camera can see and take pictures of, is likely to be much more challenging than the imaging part.
In a lot of cases, yeah. So the example with which I gave you, where is a fairly challenging material handling problem, and so the corresponding costs as well could far outweigh the imaging part, because, as I said, camera prices are reducing. Software and algorithms are getting they're following Moore's laws in terms of getting much more powerful. The cost of a computer and the capabilities of a computer are fast approaching exponential levels of performance. And so it sometimes isn't the imaging system and the vision system. It's actually the complexity and the cost is a material handling.
That's something that is very, very important for manufacturers and potential users of this technology to keep in mind.
Yeah.
And now that we have touched on that topic, that very important and sensitive topic of cost, let's talk about that a little bit more. What ballpark guidelines can a potential user of machine vision for visual inspection go by when trying to assess? I know it depends a great deal on the nature of his problem, the nature of the material handling and everything else. But short of talking to an expert like you and presenting his problem in detail to you and coming back and getting back some kind of a quotation from you, are there any even gross rules of the thumb that can go into determining whether something is going to be affordable or exorbitant? And again, I realize this depends on which part of the world you're talking about. In our country, in India, human labor is still abundant, And for most cases, it is quite affordable. So the affordability question would be much more severe, I think, in a country like India than in the US, where humans are so expensive. But even so, some guidelines on this would, I think, be very useful to our audience.
Yeah. That's $1 million question, and thankfully it's not $1 million answer, right? So the answer is a lot less than what you think. So as I mentioned, costs are dramatically coming down. Now, we've been in this business for a dozen years or so, a little bit more actually. I just got this notification on LinkedIn congratulating me on my work anniversary, and that's when I realized
congratulations.
Yeah. Thank you. So we started in September of 2008, and yeah, it's been 13 years now. So but when we started off, the cost of these primitive, or what is seemingly primitive today, algorithms and systems were exorbitantly high, and the affordability was also out of the question. And there is a number of factors that are just driving, and just like anything else, it's volumes, right? So if you produce, and if you have a demand for huge volumes, you're naturally going to drop the price with the loss of economics, when the laws of scale that come in the favor. And that's happened with vision systems as well. So there's robots, which are material handling automation, conveyors, and all those things are dramatically coming down. The cost of cameras have dropped, by almost a tenth, because they used to cost lakhs of rupees, in dollar terms, thousands of dollars, and they're now coming down to hundreds of dollars, tens of thousands of rupees, and they're going to come down even further. And software as capabilities, because of computers being very advanced and being very capable, those prices, as well have dramatically reduced. So the only part of it which was software, which was very specialized software, was the biggest cost. And it wasn't just the software, but the engineering services, because everything was very customized, and the effort to develop these solutions is extremely high, because everything needed these rule-based complex programming and rule-based solutions. Now, with simple example-based teaching with AI, all these things are starting to dramatically drop. Now, to put some numbers into perspective, right? So we've done systems as part of Qualitas, and as low as a couple of $1,000s when it comes to just the software. And they can be as high when you add these things up with material handling and all that. It can go up to even, a couple of $100,000. But, if you look at just the software alone, which, we are doing, and we are also offering software inspection as a service, and, AI-based inspection as a service, which is, as low as a couple of $1,000s a year, right? Which can easily replace a human labor and do it at a much faster and a more accurate pace. So, things are getting a lot more affordable than one thinks. It's just that you need the other elements of this to come into place. So if you already have a mature automated assembly line and things are moving in front of the camera, and you just have a simple inspection problem which requires one camera, then you can deploy these and have this automated in a few weeks, not even a few months, which earlier was the case. Do it at $10,000 or maybe $15,000, less than that total cost of ownership across 3 years. So things are getting affordable, and if you're not looking into this, you're missing out. And of course, it's a lot more lucrative in these high labor cost countries, but it's very affordable in India as well. And people are starting to look at this very seriously.
So is your $10,000 to $15,000 estimate, does that include all three pieces of the solution or just the software?
No, it's all three, a complete solution, total cost of ownership across,
very enticing
in that range. So one could, have a very robust system at something like that, and replace maybe 2 humans and get ROI back within a couple of years, within less than a year, in fact.
While that is an interesting price compared to how it was 10 years ago, I was discussing something with somebody today, which I think is even more intriguing. And it goes back to what you just mentioned now about software as a service. Now, one thing you can do is take a certain amount of recovery that you want and break it down over a number of years and offer that as the subscription cost. But could you be even more innovative and price it on a per piece basis? So supposing I'm making nuts and bolts, and these are being produced in the tens of thousands or the hundreds of thousands, and just like a nut or a bolt costs so many rupees each, would it be possible for that producer to add a little more to it, which is the cost of inspecting it? And although that unit price would probably be very low in paise, probably not even in rupees, the volumes would really add up and make it compelling for a producer like you. Have you thought about that at all?
Yeah, the thought has crossed our mind. The business models are also getting very innovative and creative, in terms of things moving to a more pay-as-you-go kind of model. And people, I think, want fast returns, right? The earlier models of pay once for a very expensive piece of equipment and then recover the cost through a CapEx model amortized over a couple of years is now changing to people offering things where you get quick value. We want returns from day one. So you want this inspection system, and then from day one, you start to realize benefits in your bottom line. And that's, moving towards more of a software services, software subscription or software as a service, or inspection as a service. So a lot of things are moving as a service. So there's a company that I recently came across. We had this interesting discussion. There's Pathfinder Robotics, and a very large company grew in the Midwest of the United States, and they're offering welding robots as a service as well. Venture funded company, doing I don't know, a couple of $1 million. And so there is a shift in terms of business models that are also starting to emerge, not just in terms of ERPs and CRMs and the other SaaSes of cloud-based SaaS software, but also in the hardware world. So it's not going to be too far down the line where that becomes the norm. But I don't think we're there yet today. We are kind of making the transition, but I think the market still traditionally is more of a CapEx model, maybe with an AMC, but we're not going to be too far when we start to realize these kinds of business models, and we are also exploring them, to be honest.
Okay, some more questions from the audience have come in as we were chatting, and our good agricultural friend Dhanush is back with another question, which is a very interesting one to me as well. It's a very simple question. Can we do without image annotation? Now, just for the audience, what he's asking is this. When you go through a machine learning exercise, you have got to teach the system what is right and what is wrong so that it can distinguish between those two when it sees new examples. And that process of teaching it what is right and what is wrong is what is often referred to as annotation. And it is perceived as a very time-consuming, labor-intensive, difficult activity. So Dhanush is wishing it away and saying, do you have any magic? Does Raghav have any magic that you can do it without annotation whatsoever?
Yeah, good question. I think Dhanush is quite plugged into the world of AI, and if you were to put a technical jargon to it, he's referring to what is known as unsupervised learning. And so in other words, you have so as imagine you're teaching a 5-year-old on what is a defect and what is not a defect. Now, there's 2 ways of doing it. You can give it a bunch of grains, which has a mixture of defects and non-defects, And you can have this 5-year-old or this 10-year-old kind of figure out on his own, oh, these things look different because they have some spots, or they're discolored, or they look different. And these, is of a different class. And so they're naturally using, what is learned from previous examples, not just grains, but maybe based on textures and colors. They'll be able to separate out the odd men from the wheat from the chaff, so to speak, right? So now, can the system really do the same without having been taught specifically that this is a defective grain of wheat versus this is something not defective? And so, but there is a lot of science and research that is going into this unsupervised learning. And there is significant progress that's being made as well. But today, 95% of systems are in supervised learning, where you do have to give it some indication, because the demands on accuracy, the complexity in these different textures and colors and shapes and forms and things like that demand some form of supervised learning. Now, but what is happening though is what used to take millions of images is now dramatically reducing. You don't need millions of images to teach is a defect identification system anymore. You don't even need hundreds of thousands. You can even do it with as little as a few hundred. And there's technology that's actually going into it, transfer learning, image augmentation, synthetic data generation, GANs, AI, which is creating images. So you have a few images, and then there's this AI system which is creating more images, and then all these images are then fed to another AI system that learns from these images, right? And it becomes better and better. So, and pretty soon you will have systems that can learn from practically no images at all, without supervised images, right? I'm talking about segregated. By supervised, I mean you've labeled these images, and so the world is moving in that direction, right? And there's some very exciting research where we are kind of following here at Qualitas, which we're keeping a close eye on things of what could be an emerging tech that we can adopt, because at the end of the day, the bottleneck, one of the bottlenecks, is this labeling and teaching process, and we are really trying to bring down that barrier and reduce the bottleneck, and literally have systems that can be up and ready in like a few days' time. So it's a great question, but I would say things aren't in that level of maturity yet. But don't be too surprised, if it comes down in a year or two.
Very good, thank you. There's another question from the audience. This time it's Ramesh, and I'll take this before I get back to my thread, where I have a few others in mind as well. So Ramesh was asking this. My question is mostly on the repeatability and reproducibility of the mounting camera. What are the types of calibration methods that one should do to ensure that positional errors during mounting and image level errors due to distortions are kept to a minimum? I think we lost your voice, Raghav. You're on mute.
Oh, sorry. Yeah, there's a lot in that question. So there is the question of how do you ensure positional accuracy of the part or the camera, so to make sure that you get consistent images. And then there is the element of how do you reduce distortion in these images.
Yes.
So when it comes to positional accuracy, I would say, machine vision algorithms and systems are at a state of the art today where they're able to tolerate a fair amount of positional accuracy in the system. So it doesn't need to be exactly in that position, because you have various location tools. So you have algorithms that can locate a part within a field of view. You just need to make sure that it's within that field of view of the camera. It doesn't go outside the field of view of the camera. So as long as you've ensured that you are more or less within that field of view, software can be used to then identify, the position, and thus, any kind of subsequent inspection that needs to happen on that part. So that's the, without knowing the specific application, I would say, that's probably not the biggest concern. The other part of it is distortion in those images. And I assume, the questioner is asking in the context of a moving part. And when a part is moving and you're trying to trigger an image without, much distortion, you have this blurred effect, then, you obviously need to make sure that the image acquisition system is designed for that, motion. So, things like using a global shutter camera, which make sure that you reduce motion blur or motion distortion, using an adequate frame rate so that, the linear speed is, within the acceptable range of the shutter speed of the camera. So things like that is probably what you need to look at to make sure that there is adequate image acquisition. Now, there's also a question of calibration, and I think this is again goes into the context of measurement. Now, it is a fact that there is, even though you have very high quality lenses, etc., the spatial distances of pixels within a certain field of view of the camera is not uniform. So in other words, if you look at, a specific physical dimension measurement of 1 mm or a couple of 2 mm, with the number of pixels representing that 2 mm varies across space in that field of view. So there's a non-linear representation of pixel distribution spatially across an image. And that's, what is due to the physics and the distortion of lenses. In order to correct it, you go through a process of calibration, which is, you typically give it a target, like a checkerboard pattern, a chessboard or checkerboard pattern of a fixed dimension. And the system learns and corrects for that distortion spatially to, compensate for these variations in spatial orientations of pixel. So that calibration is pretty simple. You have a lot of open source tools. You can also use any commercial tools which use these, but it's mostly in the context of measurement. And so, yeah, when you apply these calibration techniques, you can correct for that distortion as well. So, make sure you have adequate considerations in terms of you don't need to break your head too much in positional accuracy. Number two, make sure your camera design accounts for any kind of movement, frame rates, shutter types, shutter speed, etc. And number three, use some kind of software calibration technique to account for any kind of barrel or spatial distortion in images.
That's a good answer. Ramesh, I hope that answered your question. Give us a shout if you have any other questions. We have another 20 minutes left, so let's try and use this effectively. There's a question that somebody from LinkedIn asked, and I just want to encourage the audience and tell them at this point that Qualitas has an active social media presence today, both in terms of LinkedIn and in terms of YouTube. They have their own channels and their own subscriptions there. And you can always reach out to those forums to learn more about these topics if that interests you, and maybe even post some questions out there. The question is this: what are the considerations to easily maintain? So that is, you've already got a machine vision system, but now you want to maintain a machine vision system. How do you know if the machine vision system is working well? And how do you improve the accuracy of these vision systems over time? Good question.
Yeah, that's an excellent question. So we've seen this quite a lot, because the early adopters of machine vision, one of the number one complaint that we see is we've been sold a system that says it's X% accurate. It does all the things that it claimed to do. We installed it. Everyone was excited. And, but a few months later, that promise doesn't live up to what is the reality is very different than what it started off with. You get some changes, and then it starts to, you get a lot of false rejections. So false rejections are things which are, good, acceptable parts, which are then rejected unnecessarily. And then you just need to go and either re-inspect those parts, or worse still, you have defective parts which are then accepted. Oh, sorry. So no. So how do we then go back, and then then you got to go. You're dependent on the vendor to come and correct this. So it becomes a maintenance issue. Now, there's a couple of ways, and we've seen this quite a bit, and that's one of the, I would say, the number one complaint that I've seen from industries using machine vision. So a couple of things I would, suggest as to how we can minimize those disruptions. Now, one, there is the qualification processes and methods that you use to ensure that a vision system is working. It has to be robust and strong. What do I mean by that? Is when you teach a system or you deploy a system, make sure that you have adequate representation of all the different types of permutations, combinations of, possible defects or possible parts or possible conditions that your system would have to inspect. So, preparation here is key. So let's go back to the cell phone example. You're trying to inspect cell phones. Now, before you qualify or deploy a system and let it run autonomously without human intervention, make sure you qualify the system by using all the different types of parts of cell phones with maybe n number of defect types that you have, that you've already collected and kept as sort of this golden set that you would then run through the system and make sure that the results are as expected. So a defective part always classifies as a defect, and a non-defective part always classifies as accepted. Now, run through these not just in terms of variety, but also in terms of repeatability. So run through them multiple times. So to also ensure there's repeatability. So those are the things that you could do, before you deploy it. But having said that, even to the best of your ability, you cannot practically predict all kinds of permutations and combination, have them be ready, make sure it is working. You're always going to encounter some surprises after you've deployed it. And we've seen things like, lighting condition changes or production process changes, which now change the finish of a particular part. So what is earlier very smoothly finished is now a little roughly finished, and things start to change. Or a new part gets introduced, or a new defect gets seen, which was earlier not seen before, because now you have all this data that you're capturing, and you can actually trace back those images, or use those images to trace back your production process. So when these new things happen, you need to be alerted of this sooner than later. You don't want a customer calling you and say, hey, you shipped me this bunch of defective things. And you're like, no, wait, but I had this vision system. It's supposed to catch all these defects. And when you go back, you find that this was a new defect, which was never trained. Now, you don't want the customer telling you that this new defect was not caught. You want this caught earlier. So what we've sort of done at Qualitas, for instance, is, can we use an intelligent way? So just like you use sampling-based quality control in your manufacturing line, can we QC the QC system, right? Which is sample these images that are being inspected but sample it intelligently. So, like for instance, if there's a confidence score associated with an inspection, right? Or if we know beforehand that certain variants or SKUs are likely not going to be very accurately judged, can we sample more of those SKUs? Now, using a combination of these rules, you then collect those sampled inspected images and present it to a subject matter or a human grader and have them double check this to say that, okay, the system said it's okay, but the confidence was low. Is it really an okay part, or did it have a defect in it, or vice versa? And now with this double checking, you are then preventing any kind of mispredictions early on in the process. And you may catch these early on and then correct those, retrain those, and then make sure that these surprises are then eliminated. So we call this a human in the loop grading system that we've developed, and which works very powerfully to maintain these systems, correct errors, predict errors from happening. And it's if you're thinking that you can just deploy a machine vision system and then forget about it and then just ignore this completely, then that's very ill-advised as a process. So you need to have these systems in place, but also intelligent systems, not just do random sampling or just go once in a while and check is it working okay, but across the spectrum of these inspections, you want to sample these and then monitor these in a least amount of using the least amount of effort in order to predict and maintain and correct these systems. So that's my advice, and also a practice that we follow very effectively here at Qualitas.
So to get back to your system of what you put very nicely, QCing the QC system, are you recommending that system always be on and that it does its work once a week or once a month or some periodicity like that?
Yeah, absolutely. That should always be on. And you may, as you gain confidence and the reliability and the intelligence of these systems increase, you can throttle down the sampling rate, right? You can say, now I can inspect just what you may start off by inspecting maybe everything in a particular SKU, or you may inspect everything which is defective. But then as you sort of gain more confidence, you can throttle down that level and say, no, I'm pretty confident that this SKU is working fairly well. I have enough images and it's satisfactorily performing. And then I can just go 1%, or I can go 0.1%, or, like that. But always have it on, have some kind of a QC system. Now, and this is where technology like cloud, the internet, IoT, etc., can help, because you can have these remote deployments and this project manager or someone else is sitting in the corporate office, and these inspection systems are sending these sampled images to the cloud, and using a browser you can quickly monitor hundreds of deployments all over the factory or the world or your different plants, and then verify that, okay, these systems are working. So we've got systems which have hundreds of deployments all across remote locations in India. And the only way to make sure that these systems are performing to the peak accuracy is using, technologies like the cloud and using these intelligent grading systems, which ensures that, you are proactively maintaining and improving these systems. So yeah, have it on always, but the dynamics of how you QC this system, or the rules that govern this QC, adapt to the conditions which are necessitates the process.
Very good, thank you. I got something else on my mind. The quality systems that you are proposing, the vision systems that you are proposing, and not just proposing, the ones that you have successfully implemented in many places, they certainly are very good at catching defects that a human would otherwise have to catch, or sometimes that a human might not even be able to catch due to many reasons. But is there anything that you can do or say or contribute to actually reducing the chance of these defects even occurring in the first place? So can it do help with root cause analysis? And as a result of that, can it be used to take corrective action?
Great question, right? So the holy grail of quality control is, an ounce of prevention is worth a couple of pounds of cure, which applies here as well. And so when we, if we go back to sort of the evolution of QC and adoption of vision is the first leg of this journey is prevent this from leaving your factory floor, is catch these before they actually go either to the next process or to even to your customers at the end of the line. And then as these systems start to get adopted, you are now in a position of sitting on a gold mine of data, which is earlier, people were just using charts and they're looking at parts and we're throwing the defective ones into one bin, the accepted ones into another. And perhaps you would then go and do this manual inspection of rechecking the defective parts and trying to identify, okay, what could have gone wrong? And then sort of trace your way back into certain processes. Now, with vision, you can kind of take this to the next level, right? Now, imagine you have 10 processes in a production line. And rather than doing this one QC at the end of the line, and then trying to trace back which of these 10 processes had some process malfunction, you can have these cameras at every stage of these production processes. So now you have, near real-time inspection, which gives you an early detection and prevents the next process from happening, which may result in scrap. So there's almost like you're preventing, you're not preventing maybe the final product or that first defect from occurring, because you're still catching that first defect, but you're preventing all these subsequent value additions, right? Which results in a huge, tremendous savings. But that's sort of the next step. Now, if you take that up a level, and if you then look at these causes of defects based on image data or based on some kind of discrete data, you can then perhaps start to make sense to what is contributing to these defects. So we've seen, for instance, that there are certain times of the operation process, which is either in the late nights, the third shift, the graveyard shift, right, which results in higher defect rates, and which is telling you that it probably makes sense. You start to see that people start to get fatigued late into the night, and which is likely the cause of why certain of these defects. And so then you can start to take preventive steps to make sure that, okay, you either have some kind of a double shift or a double QC, or you increase the vigilance in those shifts to make sure that these defects don't occur. And then you start to take corrective action because you have this discrete data, right, which can be analyzed. So you're making data-driven decisions and correcting these steps. Now, you take that even to the next level and you say, can you automate this? Can you predict these defects using AI? Because now you have images that are taking images of these parts, and then you start to see patterns which contribute to a defect before they actually manifest into an actual defect. What's known as predictive maintenance or predictive analytics. And so then you have a closed loop system that throttles the parameters that go to control this. So let's say, you're doing some process automation and that the color is, as soon as it starts to reach a threshold, you need to control a process parameter that reduces maybe a heat or humidity or some kind of environmental temperature, which controls this process from producing defective parts. Now you have this camera, and then that's processing it and then sending signal back to the processing system. And you are then controlling this and preventing the defects from even happening to that extent. So, there's various levels of maturity in defect prediction, all the way from making sure that it doesn't reach your customer, but all the way from and all the way into actually making sure it's controlling the process and preventing it from occurring in the first place.
That's a very good point. It could do with some elaboration. The fact that when you install one of these systems, you also create or you also enable the generation and recording of all kinds of additional data that can then be used with a whole bunch of big data and other analytics programs which have been out there for years to tell you things that you would never be able to do if a human was doing that, because that data would never even be available. So you can think of this not only for the inspection benefits, but also as a quality improvement data generation system. And that's a very significant value.
Yeah, and data generation for offline analysis, but also real-time action and control. So that is, the power of what digital transformation really has to offer. And digital transformation in this case is just using digital images for processing and control.
I noticed that we have 3 minutes to 9, so I'll try and squeeze in one more question at least, if Aditya will allow us. And this is
there's also some questions in the Q&A, which I don't know if
yes, that's what I'm going into.
There are a few more.
There's one from Wasi in the chat. Is that what you meant? In the chat?
those. Yeah, there's one from Pradeep Kumar Ramesh.
I'll take the one from Wasi. Yeah. Can AI ML replace the existing machine vision techniques in the application to areas such as detection and calculation of various objects, various aspects, such as gauging? I think he's talking about gauging. Can AI be used for gauging?
Gauging, okay. Yeah, that's again a common question we get asked a lot, because machine vision, a common application of machine vision is gauging and measurement. And gauging and measurement, at the basic level is to identify physical dimensions. And so, real quick, we know that images are stored in pixels. So any kind of dimensions that we measure in image processing is in the form of pixels. Now, we need to translate or convert those pixels into physical dimensions like or microns or whatever physical dimensions that you'd like to measure them in. So that's at the fundamental level a gauging and measurement problem using machine vision. And for that to happen, you need to have two things done well. You need to make sure that you have a well-calibrated system so that these pixels are translatable into MM. So we talked about distortion and how they're spatially oriented in a non-linear form across an image. So you need to have very high calibration and distortion-free distortion correction in your software or hardware systems. Now, but when you look at fundamentally how AI works and the technology of AI, it's really not meant for gauging and measurement systems. And so there are some applications and technologies which are better suited using traditional classic machine vision technologies and approaches. And gauging and measurement is one such application. I wouldn't, the general answer is no, but of course, the rule of thumb to use is because humans are also doing gauging and measurement. So if you look at two different thicknesses of, let's say, any kind of packages or pouches, one which is filled and one which is empty. So you have the sachet, which is filled, and so there's this thickness. So your eyes and cognitive processing is seeing the thickness, which is essentially a gauging process that you're doing. But you're not mentally really calculating that this is, 5.3 mm to the extent that, a vernier or some kind of gauging instrument could do. And AI and ML is replacing at the fundamental level human intelligence. So it's able to gauge to the extent that a human can. But if you're looking at, a very high precision in gauging and measurement, you're better off using classical rule-based edge detection types of applications. Now, the rule of thumb we use here at Qualitas is, is the gauging precision more than 10 pixels? And if that's the case, then, AI and ML can help. But if not, then, you're better off doing something with a rule-based system. And oftentimes AI ML can be an overkill. And that's a great question, right? So it doesn't necessarily mean AI and ML is the right solution for every application you see in machine vision. And these are the sometimes wrong use of tools. When you have a hammer, everything looks like a nail kind of thing, shouldn't be your approach. So you don't go about solving every application in machine vision using AI and ML. It's also important to be judicious in selecting these applications.
And so the lesson there is, in the midst of all this AI excitement, let's not ignore the value and the applicability of traditional tools in those cases that they are still better for what they need to do.
Absolutely. AI is not replacing computer vision or rule-based computer vision. It's just solving things that traditional systems could not solve before. It doesn't necessarily mean it can do things that were done pretty well by classic computer vision rules and algorithms better.
Exactly.
It's just solving a different problem space that was very hard to do with traditional systems.
Aditya, how are we doing on time? I think it's past 9 o'clock.
Yes, that is correct. I think now is a good time to end. And once again, thanks everyone for joining. Any last words, Mr. Lucas, Mr. Agua, before we end?
No, nothing from my side. I like the fact that most of the audience stuck around with us for these pretty intense 1.5 hours. And I hope this was of some use to them, and that they will continue to engage with Qualitas over the social media channels that I just mentioned. Once again, LinkedIn and YouTube.
Yes, thanks everyone for participating, and do write to us. I'm just gonna put down our email ID in case you have any questions, and and we'd be happy to sort of get back with whatever answers we have. And on that note, I think thanks everyone. Take care, and until next time, stay safe. Thank you.
Yeah, thanks, Aditya. So I would encourage, I really enjoyed the talk. Thanks for the questions. I'd like to thank the audience for staying back. And we're always available on social media. Do engage with us on our LinkedIn profiles, Adi, if you want to share that as well. We get a lot of questions on social media, Scale mentioned. So if there's any unanswered question, I'd be happy to answer it there. I look through all the comments personally and make sure I answer them. And but in the interest of time, I guess we have to wrap it up. So thank you, and have a great night, everyone.